The starting point of the exercise would be the set of requirements. Those requirements might be in different formats. In this case, we have the requirements that were designed long ago. The company was called Tech Coaching back then. Let me change it now. The company is called EverBits. So this is the unit specification of Thermostat. TMS is the abbreviation, three-letter acronym for a heating device. TMS turns the heating device on or off based on temperature set point. We will call it a set point, SP, from temperature sensor and ready flag from the heating device. The error is actually a difference. Error is not so good name for a variable. Let's call it diff for now. From temperature sensor and ready flag from the heating device. So what we are doing now, we are reviewing the requirement before we are implementing. So I never start implementing a requirement without understanding it. So this error is now defined in the interface specification. So the first interface, this is the input type, is called a diff. So let's call it a diff. To make sure that we are talking about the temperature, I might also use here some kind of a suffix here, like diff-t or something. But for now, I just use the diff name. Then the type is input. Integer 8 is the data type. Dimension is 1. We use the full range of data type integer 8, which goes from minus 128 to 127. Ready is the other flag, which is also input, and this is Boolean, true or false. True is ready and false is not ready. And so we have the min and max values 0 and 1. The switch on is the output of the thermostat. Basically, this is the output with which we say that we switch on the heater or switch off the heater. So this is the 100% on and 100% off. Again, Boolean. And now we need some threshold data. We might use the variables true and false in Simulink and Stateflow, but in this case we choose to use the parameters off Boolean and on Boolean. Those are actually not parameters, those are actually even constants. All right, so off is 0 and on is 1. Why is that? Because we also want to use named data in the code, and it looks better, and it's also an exercise for us. So, and then the really valuable parameters would be the parameters for the threshold of the temperature. We use the off threshold, which is between minus 20 and 0. Basically, this is the threshold for the difference, right? So minus 20 and 0. And on threshold, which is also integer 8 for 0 and 20. So this is so much to the interfaces. The only thing that I'm missing is probably the unit. And so I will introduce an extra column here to define a unit. The unit for diff would be temperature, centigrades. The ready flag here is not available. Switch on, not available. Like off. Off threshold is also temperature, like on threshold, and this one is not available. So I believe now the interface is fully defined. We did not spend too much time on the interfaces, but we now have fully defined the variables. They are compliant with what we are discussing here. We also know what will be the name of the unit. And now let's look into the use case. And the use case is actually what we know right now. So let's read this. The heating device is in ready state, should be switched on. All right, so if the heating device ready state is on, then we switch on. So basically, it's about the ready flag. If the set point error, which is in our case diff, why am I doing this? Because it's easier for me to map the interfaces to the design later, is bigger than or equal to on threshold. Oh, see, we used good defined names for the variables, and so we can just reuse them here in the use case. Very nice. So bigger than or equal. So bigger than or equal is this. The heating device, I introduce caret return here so it is easier to read for me. The heating device is in ready state. This is ready. Should be switched off if the set point error is smaller than or equal to off threshold. Smaller than or equal to off threshold. Again, we have a parameter off threshold, and here smaller or equal. All right. So in other cases, and we see that they might be bigger than off threshold and smaller than on threshold. In other cases, the old state of the controller output should be preserved. So we remember what is the old state. The old state is the state at the point of time before the actual point of time. So k minus 1. If k is the actual point of time, then k minus 1 is the previous. And we might use some kind of a state to handle that information over time, that kind of history. So the heating device may only be switched on when the ready flag ready is true. Otherwise, it should be switched off. All right. So this is the use case, which is pretty well understood. I guess you also see that it is not complex. It's a simple thing. And let's now provide this text in natural language into the semi-formal notation. And see, we call this a TMS because of the name of the unit that we will develop. And this is the use case, and so we use the abbreviation use case 1. A very simple way of using some kind of a ID for the requirement. For the use case, it is done in natural language. It's difficult to implement right away. So there are a lot of interpretations possible. And so we derive the requirement out of the use case, and we preserve the use case name here and just use an extra abbreviations for the requirement. So underscore requirement 1. So now this is a requirement. And I also will use a prefix here to sum up that this is the requirement ID. And this is semi-formal notation. Why do we call it semi-formal? Because we have some kind of structural text with if, else, then, which everybody will understand. And basically we try to interpret this use case and explain it in the machine-like manner. Let's start with the beginning here and see whether it is a good requirement, whether it is actually working the way we want it to work. So the heating device is in ready state, all right, should be switched on if the set point diff is bigger or equal to on threshold. So this diff is bigger or equal to on threshold. This is diff bigger or equal to on threshold, and the ready is true. I like it. Then switch on, and switch on is our output, is set to on, and on is 1. That's correct. Otherwise, and we already did prove that the ready is true. So otherwise, we check that the setpoint error diff is smaller or equal to off threshold, smaller or equal to off threshold, and then we switch it off. And I don't like the way that how it is implemented here because we are not using this. So I would actually try to use the complete requirement here, and then when we will be modeling, we will see whether it is needed or not. Then switch on is off. And in other cases, the old state K1, old state of switch on of the controller, it says then switch on of the controller output should be preserved. And preserved means that I actually write it to the new one. And this is the switch on K is equal to switch on K minus 1. This is the else. Now it looks good to me. I do see that this requirement is not atomic. Basically, there are different requirements. This one, then this one, and this one. And so you will see in your production projects that people will separate it into the atomic requirements. But if you will try to implement it, you will see that these atomic requirements are difficult to implement because you need to, again, understand the context, and you actually lose the context if you separate it. In the ISO 26262 part 8, we have an explanation that if the requirements are not consistent, or if the requirements are complex requirements which are holistic, you should not divide them apart. And so we preserve this complex requirement, which includes a couple of conditions. But this is exactly one complex requirement. We will not separate it in different ones. In your production projects, there might be another requirement for how to do this. I actually feel like it is good enough for the first start of the implementation. You can save it. It took us 10 minutes with the discussion. Based on ISO 26262, you would go for a review, but in the test-driven development, you usually try to model this kind of requirement to see whether there are some internal inconsistencies, and you also verify this kind of a requirement and show it also in the presentation. So it's much better to implement it right away. You will not lose time with this. You just get another perspective, and it will help in the next review. If we talk about the V model, now we are at the requirement level, and we'll go into the model level. This is the implementation, and implement this requirement in the model, including that interface. See, the requirement is now just in this folder, and I know that in the production I will need a different folder structure. So let's define a folder structure. And I will develop a couple of folders. The one will be doc for the documentation and requirements. Push it to the doc. Then I will need the folder for model. It is probably enough for now, but I know that the next step will be to verify it. So I need the folder for testing, and this is sufficient for the model in the loop. But if I want to go for the software in the loop, generate C code and verify that C code, then I will also need a code folder. This will be the folder structure that we are working with. Now we open the doc and go to the modeling, and now we will start modeling with this specification. We start from scratch, opening Simulink,